Hello, everyone. Thank you for having me at the seminar. It's a great pleasure to be talking about variability, especially because a lot about the QPO, especially, has been studied and pioneered in Opava. So let's get started. I'm going to talk about variability in black holes. So where do we find them? Of course, we do have them at the center of the galaxies. I think we're going to see a picture in the evening today in the press release. But we also find them in binary systems, especially called as X-ray binaries, where you have a compact object, a black hole or a neutron star, which is accreting matter from the companion star. And this is and during this process, a lot of radiation is emitted in X-rays, and hence they are termed as X-ray binaries. So based on the mass of the companion star, these X-ray binary systems are loosely classified into low mass and high mass X-ray binaries. So most of the content that I'm going to speak about is mostly relevant to low mass X-ray binaries, but we can always chat after the talk if you're interested in the high mass X-ray binary systems. So the key components of this X-ray binary system is, of course, there's the companion star that's transferring matter. You have the compact object, and then there is this accretion disk, which is formed by the matter that is ejected by this companion star. And since this carries certain angular momentum, due to the central gravitational forces of this compact object, it tries to settle down onto a plane, thus forming an accretion disk. And then you can, and as the matter gets accreted inwards, it gets heated up, where its gravitational energy is converted into thermal energy. And the viscous turbulent forces aid in or help in transporting the angular momentum outwards so that the accretion can happen. And in this process, a lot of heat is emitted, which is eventually radiated away. Very close to the black hole, you may it's possible that you end up with the temperatures of the gas is so hot that you eventually have a very optically thin corona. I must mention that the state of the corona is quite debatable, whether it's at the very close to the black hole, or it's the base of the jet, or it sandwiches the accretion disk is something that's still a debate in the community. So moving on, these systems are, of course, when we see them in a telescope, they are like point sources to us. So how do we study them? Well, lucky us, they are quite variable. So here I'm just showing an example of an X-ray luminosity for a particular system, where you see that the luminosity varies or it undergoes an outburst on timescales of months to years. But not just that, it also does a lot more than that. So basically, during just that outburst, not just the luminosity is varying, but also its spectral its spectra is also changing. So when it starts the low luminosity state, especially when it's in the quiescent state, well, if you look at the spectrum of the system, you typically find that most of the photons peak in the hard X-ray. So that's why it's called a low hard state. And if you, as the state transits into high state, or where as the luminosity keeps increasing, you're moving from the bottom right to top left. So basically follow the arrowed paths. And then eventually you reach the soft state where the disk or the emission is completely black body-like. So you see a lot of emission in the soft X-ray region. There are also certain intermediate regions, as you can see here from the hard intermediate and soft intermediate. So you can see how the power law component here peaking in the hard X-ray region slowly transmits into the peak in the soft X-rays. Phenomenologically, the hard X-ray emission is explained by the presence of the corona that I just mentioned before, where you have an optically thin corona close to the black hole, and then the emission from the outer thin disks or the disk region is basically provides the seed photons for inverse Compton scattering, which then help in the hard X-rays emission. Well, in the soft state, you basically have the standard thin disk that everybody is well aware of, which emits black body-like radiation. The geometrical state of these intermediate regions is also not very clear. And there's a lot of work that's been going both from the spectral temporal analysis and the simulations to better understand these states. But if you have a look at the not the energy spectra, but the power spectrum, you can notice in this that during this outburst phase, there are also other small rapid variability-like features, as you can see here, which are the QPOs. Which I'm going to be talking about in this talk. And the second thing is that there is this band of power present, particularly in the low hard and the hard intermediate states. That's called the broadband variability. And this is also something that I'm going to be focusing in this talk. So QPOs, what are they? Well, it's basically everyone is aware of what a periodic variability would be like, which is you keep getting or receiving a signal at a fixed period. But the quasi-periodic oscillations are something which in which the frequency of this signal is also modulating over time. So that's why instead of having a very narrow peak, what you would see in a power spectrum is a broadened peak. There are sub-classifications of these QPOs, particularly high-frequency QPOs and the low-frequency QPOs. And as the terminology says, it's basically the high frequencies are a few hundreds of hertz, and the low frequencies are observed from the millihertz to a few tens of hertz. In this talk, I'm going to be particularly focusing on the type C QPOs, which are the most observable ones, prominently observed in the low hard and the intermediate states of the outburst. And yes, but before that, I'm going to be talking about the broadband variability, which is basically okay, I'm sorry, I forgot to mention before that if you have any questions, please feel free to stop me in the middle of the talk. Maybe it's better to clarify it then and there rather than at the end of the talk. Okay, let's move to the broadband variability. So a better way to understand what's this is, let's take a light curve. This is for a system GRS 1758 to 58. And just looking at the light curve, you can see that there is this variability on a few hundreds of time scales. So let's just take the small window and then keep zooming in. And then you keep finding variability no matter how much you zoom in, even on the scales of microseconds. So what this means is that if you make a Fourier transform of this and compute the power spectrum, you would see a broad band of this power stretching over a stretch of frequencies. So a particular way of characterizing this is that the power would vary as inversely proportional to the frequency with an index of -1. So this is the broadband variability that is usually observed in the low hard and hard intermediate states of the black hole X-ray binaries. There are also other characteristic features, not just along the power, not just the broad stretch of power in the power spectrum, but there are also other features that are exhibited by this variability, such as this strong coherence, frequency lags that I'm going to be talking about in a minute. So how is this variability explained? Well, the broadly accepted phenomenological model is the propagating fluctuations theory. And what that says is that if you have accretion rate fluctuations that are occurring on the viscous timescales at each radii in the accretion disk, and these fluctuations are propagating inwards, and also imprinting their fluctuations on the fluctuations generated at the inner radii. So basically, this imprinting behavior causes this imprinting nature causes this multiplicative behavior. So firstly, the fluctuations are generated at viscous timescales. So of course, the frequency of these fluctuations that are generated at outer radii would be way less than the fluctuations that are generated at the inner radii. And the second thing is that because of this imprinting nature, if you look at just the fluctuations or the emission from the inner radius, you can find or trace the fluctuations that are generated at the outer radii. So how can you see this in the observations is that because of this imprinting nature, what you find is if you take the light curve and then make a probable redistribution of it, you find a log normal behavior in the flux. And the second thing is if you plot the RMS variability as a function of the mean flux, you find a straight linear relation, which means that the brighter the source is, the more variability is getting. Yes. Not just that, the second thing is, well, you have emission from two different regions of the disk, because the inner regions emit in hard X-rays and the outer regions emit in the soft X-ray band. And if you compute the coherence between the signals that you get in these two different energy bands, then you find a strong coherence up to certain frequency. And this frequency basically marks the viscous frequency at the outer edge. And also, if you compute the lag between the light curves in these two different energy bands, you find that the lags are frequency dependent and also positive. What this means is that the hard to soft lag is positive, implies that the emission, the fluctuations at this lower frequency, which are thought to occur at the outer radii, are propagating inwards. That's why it's a positive lag. And imprinted on the fluctuations or the emission from the inner regions. That's why you can see still a trace of these fluctuations in the hard X-ray emission. So, well, this model, as you can see, can well explain the observations, but then is this really valid? In all these models have been developed and studied for geometrically thin disks. So the question rises, what happens to it in a geometrically thick disk? Because especially this broadband variability is observed in the hard intermediate states where we know there is a corona present, and most of this hard X-ray emission is coming from the corona. And the second question is, these models are developed based on the alpha prescription, and it's widely accepted now that the turbulence, the source of the viscosity is the MRI turbulence in the disk. And the question again comes is, can MRI turbulence sustain this propagation, or in some way damp the propagation of the fluctuations? And then the first question is whether it generates such fluctuations. So we took help of the numerical simulations to study this better in the numerical simulations. The one problem is these are timing analysis. So you, and to study the lag especially, you would need data for a run for a very long time. So we also took 5 different simulations, and as you can see, these are the simulations that we got from other works which have been done for a very long time. And these 5 simulations have been performed by different codes, and then the initial setups are quite different. So our results, in a way, are robust and not dependent on any of the initial conditions. Especially it's important because I just want to mention here that these simulations, especially A and C, as you can see, they have different magnetic field configurations. And it's been stated in the White et al. Paper that these initial conditions, different initial conditions, especially in the magnetic field configuration, can actually result in a different state, final state of the disk. For example, in this in the A or C simulations, you end up having a lot of outflows in the equatorial region, whereas the B simulation ends up having a more like mad, briefly enters into a mad state with outflows in the polar regions rather. So, well, these simulations actually are a good test for us because, as I said, we our results would be robust to the initial conditions. So, and all these simulations are non-radiative, so we cannot actually have a luminosity. What we've decided to do is use mass accretion rate as a proxy for the luminosity. And I'm showing you here the mass accretion rate onto the black hole computed for all these 5 different simulations. And you can already see they are quite variable. But it's hard to just gather information from the raw timing data. So what we do is we start looking for evidences in the features like radial coherence and the lags in the power spectrum. So the first thing on plate is the radial coherence, which is basically, it's a complicated plot. So let me walk you through this. What we do is we take the mass accretion rate at each radius and then try and then compute the coherence with the mass accretion rate at the innermost radius, which is the event horizon radius. And we see here is that the red region means the coherence is close to 1, and the blue is where you have the least coherence. And you can see that below a certain frequency, the mass accretion rate at each radius is highly correlated with the accretion rate at the inner radius below a certain frequency. And this frequency is nothing but the viscous frequency. So what this is saying is that the fluctuations that are generated, any fluctuations that are generated at a given radius above the viscous frequency at that radius are damped out and therefore do not propagate inwards, and therefore they're not correlated. Only those fluctuations that are generated below the viscous frequency propagate inwards, and hence you can find the strong correlation with the inner radius. Another proof that they're actually propagating inwards and not the other way outwards is that we see a strong, we see a positive lag when we try measuring the lag between the fluctuations at any at 3 different radii compared to the 15 Rg radius. And then you can see that the lag is constant below the viscous frequency, and anything above that you wouldn't actually have to believe the data. So the lags are indeed the fluctuations. This shows the fluctuations are actually propagating inwards. And then finally, if you look at the distributions of these mass accretion rates, you can find a nice log normal distribution shown by the blue curves. And also we find that the accretion rate from the simulations actually maintains this linear RMS mean relation. So all this is showing that the variability process is indeed multiplicative in nature. And finally, in order to compare with the observations, we use some emissivity profile with certain power law index for the emission, which varies for the hard and the soft X-ray emission. And then we try producing the power spectrum from our simulation data, which is shown here in the orange and blue curves, and try comparing it with the Cygnus X1 hard state data that we have, which is shown here in the black points. We see that the hard emission profile from our simulations, which is shown here in the blue curve, matches well with the observations. And also, when we compare the lags from our simulations to the observational data here, again in the scattered points, we find a very good agreement. We couldn't extend to the lower frequencies because for that we need the simulations to be much, much longer. All in all, the take-home message that I wanted to leave from this first part of the talk is that the mass accretion rate from these simulations indeed actually shows this propagating fluctuations behavior. And many of these characteristic features that define this broadband variability are also found just from the just in the mass accretion rate from the simulations. So it's a great check for the it's a great test for the phenomenological model. The second part of the talk, as I promised, would be on the type C QPOs. So let me go ahead with that. So the type C QPO frequencies, as I said, are the most common ones that are observed in the systems. They are they are initially observed in the low hard state or the hard intermediate state, and then they last towards the rest of the intermediate states during the outburst. The way they are characterized is that they are usually present above this broadband variability feature. And sometimes you can also see the harmonics and the higher harmonics and the subharmonics of the centroid frequency. So when you look at the centroid frequency of this QPO, it's found that it's very tightly correlated with the spectral state. So what I'm showing you is at the bottom is that the QPO central frequency for high inclination and low inclination sources varies with the variability is correlated differently with the QPO frequency for the high inclination and low inclination sources, which is suggesting that this QPO has actually a geometrical origin. And therefore, that's why it has to be it has to vary based on how the source is inclined to the observer. So the geometrical origin of this QPO is explained by this widely accepted model, which is the relativistic precession model. And what that says is you have the, well, before that, any tilted orbits around a rapidly rotating object, in our case, a black hole, experiences the lens steering torque, which is basically due to the frame dragging effect. And this causes this particle's orbit to precess around this rotating object. So this has been extended to explain the type C QPOs by Stella et al. In 1999, where and then further it has been extended by Ingram and Fregel and others to actually make the torus or the hot corona that you have in the hard states that is undergoing the precession as a solid body around the black hole spin axis. And this is thought to, and this precession frequency is actually around few millihertz to few tens of hertz. That explains these type C QPOs. There are also other models that are in the market that are that explain the type C QPOs based on oscillatory shocks, C modes, and other models. But this model is widely accepted for the reason that it has this geometric origin for the emission of the QPO. And there has been support from GRMHD simulations that have been performed in the past 1-2 decades, which show that the thick disk indeed persists as a solid body. If it's a thin disk, what you would expect is actually that the disk would align with the spin axis of the black hole because of this Barden-Peterson effect. And it has been confirmed by the simulations again in a couple of years back. But if we just remember at the initial phase of the talk, we always have a thin disk. We always have some emission in the soft X-ray part. So we know we have thin disk in the outer regions at least. So this torus that is precessing close to the black hole must be ending somewhere, and it should be meeting the thin disk. Now the question comes, how does this thin disk that is sitting outside affects the precession? Because so far, all the work that has considered the precession as a source for these QPOs has only considered the torus, an isolated torus, and all the simulations that have been performed so far have only performed isolated thick disks. So that's where our work comes in, which is basically performing GRMHD simulations of misaligned disks, but also they are truncated. So here is a initial snapshot of our simulation where the disk is, the initial angular momentum of the disk is aligned in the z-axis plane, along with the z-axis. The black hole is misaligned by 15 degrees in the minus xc plane. The red region is basically the thick disk, and the blue region is the thin slab. We decided to start with such a setup because it's much easier to develop the two component flow rather than starting with either a thin slab and let the MRI do the job to expand it to a thick disk, or the other way around, where you start with the thick torus and then try the cooling prescription do the job to collapse to a thin disk. So we thought this would be much easier, and then it worked. And then the black hole that we have is a spinning black hole for 0.9, and the resolution is roughly 384 by 256 by 256. Let me show you the movie. So what we find is that the inner regions indeed precesses, which you can see in the almost reddish area, and the outer regions also start to precess slightly. And we will talk about why the outer regions are precessing in a minute. But before that, it's a valid question that actually we start with such a setup, but do we maintain the two component flow? So indeed we do. What I'm showing you here is on the left plot, I'm just giving you an idea of how the midplane looks like at 5,000 gravitational time units, and at much later in the simulation at 25,000 gravitational units. So you can see the inner region is quickly misaligned and precesses way quicker than the outer regions. The outer regions are also misaligned. But if you look at the scale height at these different radii, you find that the innermost region is, of course, quite thick with a 0.5 scale height. And as you go out, the thin disk region is almost maintained at the same height as what we have initiated it with. So yes, the cooling is actually doing a good job here, and the two component structure is maintained throughout the simulation. So to study the misalignment, the first thing we can, there are two quantities that help us, which is the one of them is the tilt angle, how much misalignment, what is the misalignment of the orbit. And in our simulations, what we found is that the inner regions are, of course, more misaligned compared to the outer regions. And the outer thin disk regions are actually are at the same or almost close to 15 degrees that we have initially initiated the simulation. So, and the second question is and the second point is that this misalignment is actually constant, nearly constant in time, but then of course it decreases with the radius, as I said. And the second thing is the precession. How much has this orbit precessed around the black hole spin axis over time? And in our simulations, so this is a space-time plot, which is basically x-axis is showing you the radius and the y-axis is showing you the evolution in time. And the color is representing how much color is representing the precession angle measured in degrees. So you can clearly see for a bending wave here, which is basically through which the warpness is communicated in the disk regions. And then here in the inner regions, you can see that the torus is almost precessing as a solid body, which is what is expected in a thick disk. And of course, but there is a catch. But before that, you can also see that the outer thin disk regions are also precessing. You wouldn't expect the outer thin disk regions to precess, but the reason that's probably happening in our simulations is because the lens steering time scale is greater than the sound speed time scales in our simulations, basically throughout the simulation domain. So if this is the case, then yes, the outer regions could also be subjected to the lens steering precession. But the precession rate is way slower. So it seems like the outer disk indeed affects the precession of the inner regions. So what I'm showing you on the right is, let's say we integrate or we average the precession angle over the inner regions from the inner radius to 15 Rg. That's where the truncation radius is. And that's from this 0.9 simulation that I've been showing you, which is the solid green curve. And the black dotted line is showing you what is the expected precession rate. So the expected precession rate for this torus extending from some inner radius to outer radius, which is 15 Rg in our case, is the lens steering precession frequency weighted with the angular momentum of each annulus in the disk. And that's what this black dotted line is. And you can see that initially, the torus actually precesses at this rate. So you can see the green solid curve is following the black dotted line, and then immediately it decreases and starts precessing at a very slow rate. And this rate is actually 95% less than what is expected. So you see a relative decrease of 95% in this precession rate. What this means is for my 0.9 spin black hole, I would expect around 16 Hertz frequency for the torus size I'm considering. And what I actually get from simulations is around 0.74. So it's more than an order of magnitude less. We've also done some, sorry for that. We've also done some low resolution simulations, which are shown here in the orange and the blue for 0.9 again, but and the blue curve is for the 0.5 spin black hole. And we see similar, and the result is qualitatively similar in all these simulations. So the main important message is that the outer disk does affect the precession rate. And the reason why we think this is happening is because the thin disks are actually known to damp the bending waves and cause, because of the viscous diffusions happening in the thin disk, there's a lot of misalignment, there is a lot of alignment happening in the thin disk region. So another way to understand is if the lens thinning torque that is applied to make the precession happen, if that is used to actually transport the angular momentum, then the lens thinning torque actually that is available to make the precession happen is less. So indeed, your precession rate would decrease. So that's one way we kind of understand it. If you look at the angular momentum flux in the plane that's perpendicular to the black hole, in which the lens thinning torques are actually acting, we can see that in the very initial phases, as soon as this bending wave reaches the thin disk, there is an increase in the angular momentum flux. And also, interesting thing is you can see it's more in the x direction, x component, where you can see an inward angular momentum flux from 30 Rg towards the transition regions, and when we look back at the precession rate, it seemed like the 30 Rg at the 30 Rg initially there is certain the annulus precesses by certain amount, and then it stalls, and probably that's because the net effect on the precession by the lens thinning torques is actually zero. So there's no more precession happening at this 30 Rg outer radii. The inner radius, the inner torus, and certain transition region does undergo precession. But as you can see, probably because of this increased angular momentum flux, the lens thinning torque is not fully being applied or used for the precession. So that's why there's a decrease in the precession rate. Apart from that, but there is a lot of variability we found in the misaligned accretion disks. So what I'm showing you here is the mass accretion rate for all these three different misaligned simulations that we perform. And the red dotted is the untilted or the aligned truncated disk simulations that we performed. So the top panel is showing you the mass accretion rate in the torus region at 5 Rg, and the bottom panel is the mass accretion at 25 Rg, which is way out in the thin disk. And we can find a very clear signature of oscillations in this in the accretion rate in the thin disk region, and this is only present in the misaligned accretion disk. So somehow the misalignment is probably causing these oscillations in the accretion rate. And if you look at the power spectrum for these simulations again, where the x-axis is the radius and the y-axis is the frequency, and the color is showing you the power in the log scale, which is multiplied with the frequency. So what you can see is these QPO-like features that are present in the thin disk region. There's a lot of power present along the Keplerian curve for surely, but there are these QPO features definitely which are related to these oscillations that we see. And we also found that there are vertical oscillations. So what I'm showing you here is the mid plane at certain azimuthal angle, which is 0 here. And how because the mid plane is tilted, it's not always at pi/2. So I'm looking at how this mid plane is oscillating at a particular azimuthal angle. And then you can see that it's indeed undergoing this nice oscillations in all these simulations. And the amplitude of these oscillations decreases as you go further and further out in radius. So if you if it's vertical oscillations, then we should find some similar variability features in its vertical velocity. And what I'm showing you here is the power density spectra again of vertical velocity or the poloidal velocity component. And again, you can see these nice QPO-like features in the inner region at 2 × 10⁻³ gravitational units, and probably a harmonic of it is 4 times 10 to the power minus 3. Interesting point is that you see this 2 times 10 to the power minus 3 feature in all the simulations, even in the 0.5 simulations. Although it's quasi-periodic, so it oscillates between 2 and near to 2, but it seems like this feature, whatever it is caused by, is independent of the spin, but we are not very sure of this. Another thing is that this feature for a 10 solar mass black hole would convert into 40 hertz. So it's on the high end of the type C QPO, or the lower end of the high frequency QPOs maybe. We are not quite sure. So here are the questions that we are struggling with, and I would be happy to hear suggestions or ideas from the audience. We are trying to understand whether these modes are actually trapped. They seem to be trapped in the inner regions, but we're not quite sure. We're trying to understand whether these modes are actually inertial or acoustic. Also, if these oscillations that we see in these vertical oscillations, if they are any way related to the oscillations that we found in the accretion rate. Also, it would we are trying to understand the nature of these modes. For example, whether they are axisymmetric or non-axisymmetric. So yes, the nature and the origin of these modes is still a mystery to us. But the interesting thing is we do see clear variability features in the misaligned disks, and we, as shown here, there is nothing present in the disks that are aligning. So apparently they are quite boring compared to the misaligned disks. So I'll leave the take-home message here, which is basically a couple of things. One is the outer thin disk does affect the precession rate, and this has to be considered when using the model of isolated torus to compare with the type C QPOs from observations, especially because we see that the precession rate decreases by 95%. The interesting part is that the misaligned disks are more variable, especially the variability lands up with the frequencies that are seen in the black hole X-ray binary systems. So I'll conclude my talk here, and I'm open for questions. Thank you.
Thank you, Deepika. So it was a very interesting talk. So are there any questions from? You can just turn on your microphone or raise your hand.